Hello guys, thank you so much for being with me in another machine learning tutorial video. In the previous video we talked about logistic regression. In this session we will talk about the softmax function of neural networks. Softmax classification is actually the multi-class logistics in which the cost function has been changed. This will be a good foundation for neural networks. The training of these types of networks will not be different from what we have learned so far. With the help of metrics calculations, we can perform multi-category logistic calculations only once. We have up to m input data in this class. X is a matrix with m rows which are inputs, and n is the number of our features. From now on, we separate the biases and show them as a separate vector. We also put the parameters in a separate matrix. Each vector becomes a column of this matrix. I have not shown the bias vector in this figure, but we will have a bias number for each classifier. These two vectors are multiplied together and finally predictions are made. The product is the score matrix. S1 is the score for the first input. There are three numbers in S1. The first number is the score for the first class, the second number is the score for the second class, and the third number is the score for the third class. So with the matrix multiplication, we have done all the calculations at the same time. Suppose this time we want to solve the problem of recognizing handwritten digits. We have collected some of these handwritten figures written by different people. We have 10 classes here. If we zoom in on each entry, we see that each one is an 8 in 8 matrix. The houses of the matrix are numbers between 0 and 255. We have shown 0 in white, and the closer they get to 255, the closer we get to black. Here we have 64 features. Here we have to flatten everything and show it as a vector. So 64 numbers are given as input to the classifier. The output is 10 classes, so we need 10 total spheres, and we have to calculate 10 points for each entry. We have implemented the prediction function here. From now on, instead of a theta matrix, we will write W matrix, and instead of a theta 0 vector, which were the biases, we will write B. This renaming will make implementation easier. The W matrix in this example is a 10 in 64. B is also a vector of 10, which is a column vector. X is also an input. We show the entries in the X matrix as rows. The process is also called batch processing. The first thing we do is multiply the X matrix by the weights, which are W, and sum it by bytes. The result represents the points, and then we do a simple maximization. Axis is equal to 1 because we have to take the maximum in the horizontal direction. However, we do not want maximum here. We want to know in which class these points are maximum. Then we use argmax. In fact, when we multiply X matrix by W matrix, in fact we multiply this X matrix by each parameter. The first parameter, which itself has a vector W, in fact we are doing multiplication. We call theta 1 here W1. The geometric interpretation of inner multiplication in linear algebra is similarity. The larger the number of the inner production of two vectors, the more similar the two vectors are to each other. The internal product of these two vectors is equal to the size of the vector x multiplied by the size of the vector w, the product of the cosine of the angle between these two. For now, assume these vectors are equal. That is, they are at the same size. The greater the similarity between the two means that the size of the cosine of the angle between the two is closer to 1. That is, the angle between these two vectors is closer to 0. This means that these two vectors are parallel. We perform all these calculations in matrix multiplication at the same time. In the case of 1 by 1 inputs, these similarity calculations are performed at the same time. In the last stage, we have maximization where the similarity is greater. Our prediction of belonging to the class is that class. We said that we should have classifiers as many classes as possible. For example, 10 separate classifiers that have nothing to do with each other, and their outputs are numbers between 0 and 1. Because after obtaining the points, we apply a sigmoid function on them, and the sum of these numbers will not necessarily be 1 because these classifiers are independent of each other. Now we want to make the sum of these probabilities equal to 1. I want to combine all of these classifiers, and instead of having a K2 binary classifier, we have a K classifier. For this, instead of the sigmoid function, we must use softmax function. That is, we give the final scores to the softmax function so that they become probabilities that add up to 1. That is, in this case, we will have a probability distribution. Suppose you have 10 points corresponding to the ith data. We assign these points to the softmax function, which is the probability of belonging to 10 classes. When the input of the function is a vector, the output will also be a vector. For example, in this example, we had 3 classes, so we calculated 3 points. These data are part of the CIFAR10 database. Suppose this image has 32 in 32 bits. This is an image processing issue. That means we have 3072 features. We multiply these 3072 features in the weight matrix and calculate these 3 numbers. Inner multiplication can have a positive or negative result. If the vectors in the inner products are not normal, the size of the inner product can be between negative infinite and positive infinite. Now we want to convert these 3 numbers into 3 positive numbers smaller than 1, the sum of which is 1. For this, we consider these powers of E, because the output of the E function cannot be negative, and now these have become positive numbers, and now we have to normalize it so that it becomes a number between 0 and 1, which adds up to 1. For this, we have to divide each of these numbers into the sum of these 3 numbers, and now we have reached the goal, and this is the function of softmax. We wanted to define a new cost function, and now this W matrix reaches its optimal value from minimizing this cost function. The data actually belongs to the cat class, but you can see that the car score is maximum here. so the prediction will be wrong. So now we have to do something to maximize the probability of the image belonging to the cat class. This error occurred because the algorithm was not properly trained. Instead of maximizing these probabilities themselves, we can maximize their logarithm. We want to define a cost function. The cost function is what we need to minimize. So instead of maximizing the logarithm of these probabilities, we minimize the negative of the logarithm of these probabilities. So we got the new cost function. The main idea is to convert points into probabilities. This is Li, the error, and the cost for I data. Now, what is the maximum and minimum amount that this Li can take? The best case would be for this cost to be 0. This softmax function is the generalized state of the logistic. The worst case is that this cost is positive infinite, very large amount, and now we want to minimize these errors and costs. In the Python files I have put the implementations for you. Be sure to pay attention to the tips, solve the exercises carefully. You are now able to solve these exercises with the knowledge you have acquired. In the implementations I have labeled y with a vector, and for this I have used the one-hot vector method. Instead of representing y as a number, I have represented it as a vector. This can make implementation easier. The first thing we have to do is to get the probabilities from these points using the softmax function. Then we get the cost function from these probabilities. Since only one of these implies is 1, the rest of the cost function sentences are omitted. So this formula is simplified. This function is also called a cross entropy cost function. We have a probability vector P containing numbers whose sum is 1. The entropy of this vector is represented by P by HP and calculated with this formula. You can see that it is very similar to the formula of this cost function, with the difference that we have two vectors in this cost function. In fact, we are calculating the similarity between these two vectors together. We want to obtain parameters that maximize the likelihood. The same parameters also maximize the logarithm of probabilities. Now we got acquainted with the softmax classifier, which we have to train. For training, we should not do anything except minimize the cost function. For this minimization, both gradient descent method and any of the advanced optimization methods can be used. We have a training set. X's are inputs and Y's are available outputs. The things we want to learn are the parameters. We are parameters, and W's are parameters, and B are biases, which are vectors of real numbers. Now we have to get the cost of these parameters by minimizing this function. We always consider regularization to avoid overfitting. In this formula we have used L2 for regularization to minimize this cost function. It is enough to take the differential of this function in terms of W and B parameters. Here we have simply replaced the parameters and now we just need to differentiate. Here I have explained the differential for one of the cost functions. The overall differential of the cost function is equal to the sum of the differentials of the cost functions. So for every from 1 to c, we must calculate the differential of this function with respect to w. Here we have a nested function. L is a function of P and P is a function of S and S is a function of W. In these cases, we can use the chain rule in differentiation. Here we have divided the problem into two cases because the differentials will be different only in these two cases. Of these three differentials, two are very simple and the other one is almost simple. Because you've seen it before, the last differential is similar to the sigmoid function differential I explained earlier. This expression becomes simple and finally you see the simplified formula. In the same way, the differential can be calculated for any other than yi. Finally, these differentials are very simple. Now that we have the differentials, we can use the gradient descent algorithm and update the w's. As we said before, we have three types of gradient descent algorithms. Here we use the stochastic method. Now whether we really get the optimal solution or not depends on whether our function is convex or not. Here the function is convex. During training, when the training algorithm is not finished yet, we have three columns. Each of these columns corresponds to a class. This shape, this figure actually is not very accurate. I hand drawn this figure for tutorial purpose only. We choose one of the data at random, so the correct class is the yellow class and the other are incorrect. For the right class, we update with this formula. PYK is a probability, so it means a number between 0 and 1. Suppose if it is 1, it means with certainty that this data belongs to the yellow class, so this sentence becomes 0. That is, there is no need to update, but if it is 0, the most update happens. It also has intermediate states. Suppose PYK is equal to 0.5. WK is updated by a factor of input. If this data belongs to other classes, these updates should be so as to move away from this class. The value of PYK is equal to 1 when the probability of other classes is 0. These updates happen against the direction of inputs because both alpha and PYK are positive numbers. We have to repeat this for different data. Finally, we reach a point where these converge. It means that any data we give to the algorithm will be classified correctly. That is, the algorithm converges. This description represented a neural network with one layer. In the next video, we will add more layers to this network. And now, why should we add these layers? Because our activity function gives us a linear decision boundary. But in practice, we need a nonlinear decision boundary for this. We need to add a series of higher level features. The problem is that the number of second order features will be approximately 2000. Of course, we cannot have the best decision boundary with second order features. We also need third order features. The number of these features is about 40,000. As the rank of features increases, the number of these will gradually increase. Although we can make these features more and more, but if the inputs are larger, for example in color images, the need for higher order features becomes more and more, and the number of these features increases exponentially. In this way, the number of features increases. Original images are very large in the real world. For example, you only have a few million first order features, and in this order the number of features is very high. It is true that with regularization we can remove useless features, but L1 can learn which features should stay in the algorithm and which should be removed if it has enough data to train. Therefore, we need more layers to calculate all these features. These networks learn the required higher order features, but now, how do they do it? By adding intermediate layers. This is the same layer that is supposed to obtain higher order features. By combining the raw input features, it is possible to have several hidden intermediate layers. I will explain more about these in the next videos, but for better understanding I will give you an example. We have two hidden layers here. You can see that you have a circular decision boundary. This boundary is nonlinear. To reach such a limit, one way is to use softmax, which is not a good method. Another method is to entrust this training to multi-layer neural network. You can enter this address of you can use actually this Python files to practice. Neural networks are the best practice today in many real world machine learning applications. In the Python files I have included the implementation of classifiers for the problem of recognizing handwritten digits. I emphasize again that you must pay attention to these files. I highly recommend you not to miss upcoming lectures because many practical and important tips are awaiting for you inside them. Have a nice day.